Welcome! In this session, we'll explore LeetCode problem number 670, titled Maximum Swap. This problem challenges us to maximize the value of a given non-negative integer by swapping at most two digits. Let's dive in and understand the approach to solve it efficiently. The problem we're tackling is to maximize the value of a non-negative integer by swapping at most two of its digits. Essentially, the goal is to find the largest possible number you can create by reordering two digits, if necessary. For input, we're given a non-negative integer called number, which falls within the range of 0 to just under 100 million. The output should be an integer representing the highest value that can be achieved after performing the swap. To make things clearer, let's look at an example. If number is 2736, we can swap the first digit, which is 2, with the third digit, which is 7. This would result in 7236, which is the maximum possible value for this input. So, the output for this case would be 7236. In another example, if number is 9973, the number is already in its largest possible configuration, meaning no swaps are needed. Therefore, the output would simply be 9973. This illustrates that sometimes the input may already be maximized, and the solution should account for this. Now consider the case where number is 12,345. Here, we can achieve a larger value by swapping the first digit, which is 1, with the last digit, which is 5. This gives us the number 52,341, which is the maximum possible value for that input. To summarize, the constraints for the problem are as follows. Number is always between 0 and less than 100 million, and the input will not have any leading zeros unless the number itself is 0. Additionally, you are allowed to swap at most two digits, so the solution needs to optimize within those limits. Let's also consider a few edge cases. First, if the input is a single-digit number, like 7, there's no way to perform a swap, so the output remains 7. Similarly, if the digits of number are already arranged in descending order, like 9876, no swap is needed, and the output stays the same. On the other hand, if the digits are in ascending order, such as 1234, a swap is required to maximize the value. Here, swapping the first digit, 1, with the last digit, 4, results in 4231, which is the largest possible number. Lastly, for the smallest possible input, 0, there's no change needed, and the output remains 0. These examples and edge cases showcase the range of scenarios your solution must handle, from straightforward cases to those requiring careful consideration of which digits to swap. To solve the maximum swap problem, the goal is to maximize the value of a given non-negative integer by swapping at most two digits. The first approach we considered is the brute force method. Here, the idea is to generate all possible numbers by swapping every pair of digits and then choosing the maximum among them. To do this, we first convert the number to a list of digits, iterate over all possible pairs of indices, perform the swap, compute the resulting number, and track the maximum value encountered. While this method is straightforward to implement, its biggest drawback is the computational expense, especially for numbers with many digits. The time complexity is n squared, because of the nested loops for all digit pairs, though it uses constant space. Next, we have the optimized greedy approach, which is the strategy we'll focus on. This method avoids unnecessary swaps by identifying the best possible swap to maximize the number. Instead of iterating over all pairs, we track the rightmost occurrence of each digit from 0 to 9. The main observation here is that to create the largest number, we should swap the leftmost smaller digit with the largest possible digit that appears later in the number. This insight forms the foundation of the optimized approach. Using the optimized greedy strategy, we can efficiently find the best swap by leveraging the last occurrence of each digit. The process begins by converting the input number to a list of digits. Then, we create a dictionary to store the rightmost index of each digit. This allows us to quickly identify potential candidates for swapping. As we traverse the digits from left to right, we check if there is a larger digit, starting from 9 and going down to 1 greater than the current digit, that appears later in the number. If such a digit exists, we perform the swap and immediately return the resulting number. If no advantageous swap is found throughout the traversal, we return the original number as it is already the maximum. This method is highly efficient, with a time complexity of n, due to the single pass over the digits and constant time lookups in the dictionary. However, it does require O(n) space to store the dictionary. While this approach is slightly more complex to implement compared to brute force, it directly targets the optimal solution, eliminating unnecessary computations. Other alternatives, such as recursive backtracking or dynamic programming, were also considered. Backtracking guarantees correctness by exploring all possible swaps recursively but is computationally similar to brute force. Dynamic programming, on the other hand, uses a structured approach with a table to optimize swaps, but it introduces unnecessary overhead for this problem. The optimized greedy approach stands out as the best strategy for this problem due to its balance of efficiency, simplicity, and clarity. By focusing on the key insight of tracking the last occurrence of each digit, we eliminate unnecessary computations while ensuring the optimal solution. This reduces the time complexity from O(n) squared in the brute force method to O(n), making it far more scalable for larger inputs. Compared to brute force, which is easier to implement but computationally expensive, the greedy approach is both practical and elegant. Other alternatives, such as dynamic programming and recursive backtracking, offer no significant advantage over the greedy method. In fact, they add unnecessary complexity without improving performance, making them less suitable for this problem. By adopting the greedy strategy, we achieve an optimal solution with minimal overhead, making it the most effective and efficient choice for solving the maximum swap problem. The maximum swap problem challenges us to create the largest possible number by swapping at most 2 digits in a given non-negative integer. Our goal is to determine the maximum value achievable after such an operation. To solve this efficiently, we use a greedy approach that focuses on digit manipulation. The first step is to convert the number into a list of its individual digits. This transformation allows us to easily access and manipulate specific digits for the swapping process. For example, if the input number is 2736, we convert it into a list of characters 2, 7, 3, 6. This sets the foundation for the subsequent steps of the algorithm. Next, we create a rightmost index map to store the last occurrence of each digit from 0 to 9. This map helps us quickly find where the digits are located in the list. To build this, we traverse the list of digits from left to right, recording the index of each digit. For instance, with the digits 2, 7, 3, 6, the resulting map would be 2 o'clock, 7, 1, 3, 2, 6, 3. This step is crucial because it allows us to optimize the search for a larger digit to swap with the current one. After building the map, we iterate through the list of digits to find a valid swap. For each digit, we check if there's a larger digit that appears later in the list. Using the rightmost index map, we can quickly determine whether such a digit exists and its position. For example, starting with 2, we find that 7 is already in place. Moving to the digit 3, we see that 6 is larger and occurs later. We then perform the swap, which transforms the list into 2, 7, 6, 3. Now that we've performed the swap, the next step is to convert the updated list of digits back into an integer. This gives us the final result. For example, after swapping 3 and 6, the list 2, 7, 6, 3 is converted back to the integer 2763, which is the output. It's also important to account for edge cases in this problem. If the number is already the largest possible, such as 9876, no swap is needed. Similarly, if all digits are the same, like 1111, no swap can be performed. Single-digit numbers, such as 5, remain unchanged as well. These edge cases are inherently handled by the algorithm since no valid swaps will be identified in such scenarios. The key insight behind this solution lies in the greedy approach, which ensures that we maximize the result with just one swap. By always prioritizing the largest possible digit for the swap, we achieve the optimal result efficiently. The use of the rightmost index map is critical here, as it allows us to look up the position of a digit in constant time. This makes the algorithm highly efficient, with a time complexity of O(n), where n is the number of digits in the input number. The space complexity is O(1), because the rightmost index map has a fixed size of 10, regardless of the size of the input. This approach is far superior to a brute force method, which would involve generating all possible swaps and checking the maximum value, resulting in a time complexity of O(n)². This algorithm is robust in its handling of edge cases. For instance, when the number is already maximized, such as 9876, no swap is performed because the greedy check reveals no larger digits to swap. In cases where all digits are identical, like 1111, no swap is possible, and the number remains unchanged. For single-digit numbers, the algorithm naturally skips any swapping steps since there are no other digits to consider. The data structures used in this solution include the list of digits for easy manipulation and the rightmost index map for efficient lookups. Together, these components ensure the algorithm is both simple and highly effective. To see the algorithm in action, let's walk through an example with the input number 2736. First, we convert the number into a list of digits, 2, 7, 3, 6. Next, we build the rightmost index map, which is 2 o'clock, 7, 1, 3, 2, 6, 3. Starting with the first digit, 2, we check if there's a larger digit later in the list. No such digit exists, so we move on to 7, where the same conclusion holds. When we reach 3, we see that 6 is larger and occurs later in the list. We swap 3 and 6, resulting in the list 2, 7, 6, 3. Finally, we convert this list back into the integer 2763, which is the largest number achievable with one swap. The output for this example is 2763. The solution to LeetCode problem number 670, maximum swap, is implemented in the function maximum swap. Here's the step-by-step breakdown of the code. 1. Convert the input to a list of digits. The input number is converted to a string and then to a list of characters. This allows easy manipulation of individual digits. For example, if number is 2736, digits will be 2, 7, 3, 6. 2. Store the last occurrence of each digit. A dictionary last underscore occurrence is created where the keys are the digits, converted to integers, and the values are the indices of their last occurrence in the list. This helps us quickly find the last position of a specific digit. For example, for 2736, last underscore occurrence will be 2 o'clock, 7, 1, 3, 2, 6, 3. 3. Iterate through the digits. We loop through the list digits from left to right. For each digit, we check if there's a larger digit in the range 9 down to the current digit that occurs later in the list. 4. Perform the swap. If a larger digit exists and it appears later in the list, we perform the swap between the current digit and the larger digit. For example, for 2736, when checking the first digit 2, we find that 7 is larger and appears later. Swapping 2 and 7 gives 7236. 5. Return the result. After performing the swap, the list digits is converted back to a string and then to an integer. This integer is returned as the result. If no swap is performed, e.g., the number is already the largest possible, the original number is returned. This algorithm is efficient with a time complexity of O(n), where n is the number of digits in the input. The dictionary lookup and iteration ensure that we can quickly find the optimal swap, making the solution both elegant and fast. Here, we start with the Java implementation of the maximum swap problem. First, we convert the given integer into an array of characters, where each character represents a digit. This makes it easier for us to work with individual digits. Next, we create a map to store the last occurrence of each digit in the number. This map will help us quickly identify where a specific digit appears for the last time as we traverse the array. For this, we iterate through the digits array and store each digit along with its index in the map. Once the map is ready, we begin traversing the digits array from left to right. For each digit, we check if there exists a larger digit that appears later in the number. To do this, we loop through potential larger digits, starting from 9 and going down until the current digit. If we find such a digit and its index is greater than the current position, we swap the two digits. After the swap, we convert the modified character array back into an integer and return it immediately, since we've achieved the maximum possible value with one swap. If we complete the loop through all the digits without finding any opportunity to make a swap, it means the number is already the largest it can be. In that case, we simply return the original number as the result. This approach ensures that we only make one swap, and we do so in a way that yields the maximum possible value. The implementation is efficient because we use the map to quickly locate the last occurrence of digits, and the nested loops are designed to stop as soon as a valid swap is made, avoiding unnecessary computations. To solve this problem, we start with the input number, 2736. First, we convert this number into a list of its digits, giving us 2736. Next, we create a dictionary called last_occurrence that maps each digit to its last position in the list, resulting in 2 o'clock, 7, 1, 3, 2, 6, 3. This helps us quickly figure out where a particular digit is located. Now, we begin traversing the list from left to right. Starting with the first digit, 2, we check if there's a larger digit that appears later in the list. To do this, we iterate from 9 down to 3, just above 2. When we reach 7, we find that it exists in the dictionary, and its position, 1, is greater than the current index, 0. This means we can swap 2 with 7. After performing the swap, the updated list becomes 7, 2, 3, 6. Finally, we convert this list back into the integer 7236 and return it as the result. Now, let's look at the input 9973. We start by converting it into a list of digits, 9973. The last_occurrence dictionary is created as 917233. As we traverse the list, we begin with the first digit, 9. For this digit, we check for a larger number by iterating from 9 down to 10, which has no valid values since the digit is already the largest. No swap is performed, so we move to the next digit. The second digit is also 9, and the same logic applies, there's no larger digit to swap with. Continuing on, the third digit is 7. Here, we check for a larger digit, like 8 or 9, but neither is available. Finally, for the last digit, 3, there are again no larger values. As no swaps occur throughout the traversal, the list remains unchanged. Converting it back to an integer gives us the result 9973. Finally, consider the input 1234. We begin by converting it into a list of digits, 1, 2, 3, 4. The last_occurrence dictionary is created as 1 o'clock, 2, 1, 3, 2, 4, 3. Starting with the first digit, 1, we check for a larger digit by iterating from 9 down to 2. When we reach 4, we find that it exists in the dictionary at index 3. This allows us to swap 1 with 4. After performing the swap, the list updates to 4, 2, 3, 1. Converting this list back into an integer gives us the result 4231, which we return as the final output. To analyze the time complexity of this solution, we break it down into its core steps. First, the input number is converted into a string and then into a list of its individual digits. This operation depends on the number of digits in the number, which we denote as k, resulting in a time complexity of OK. Next, we build a dictionary called last_occurrence to track the last index of each digit from 0 to 9. Since this involves iterating through the digits list once, this step also takes OK time. After that, the algorithm enters the outer loop, which iterates over each digit in the list, running k times. Within this loop, there's an inner loop that checks for a larger digit to swap with. However, the inner loop is limited to at most 9 iterations, as it only checks digits from 9 down to the current digit plus 1. This range is fixed, meaning the inner loop runs in constant time, or O1. Continuing with the time complexity, once a swap is identified, we convert the modified digits list back into an integer. This operation involves OK time, as it processes each digit. Combining all these steps, the outer loop runs OK times, and within it, the inner loop runs in O1 time per iteration. Therefore, the total time complexity becomes OK *O1 plus OK, which simplifies to OK. Here, k represents the number of digits in the input number. Moving on to space complexity, the most significant contributor is the digits list, which stores all the digits of the number as characters. This requires OK space. Additionally, the last_occurrence dictionary stores the last index of each digit, but since there are only 10 possible digits, the dictionary uses constant space, or O1. In terms of additional space, the algorithm uses a few auxiliary variables for iteration and temporary storage during the swapping process. These variables occupy constant space, or O1. When we combine these factors, the overall space complexity is O(k), dominated by the digits list, as the dictionary and auxiliary variables use negligible space in comparison. To put this in perspective, let's compare it with a brute force approach. A naive solution would involve generating all possible swaps of two digits, which results in approximately O(k²) combinations. For each combination, converting the digits back into an integer would take O(k), leading to an overall time complexity of O(k³). In contrast, our current solution uses a much more efficient approach by identifying the best swap in a single pass with the help of the last_occurrence dictionary. This optimizes the time complexity to O(k), a significant improvement over the brute force method. Finally, let's explore the best, average, and worst-case scenarios for this algorithm. In the best case, the number is already the largest possible permutation, such as 9876. Here, the algorithm simply traverses the digits without performing any swaps, resulting in a time complexity of O(k). In the average case, the algorithm identifies a swap and terminates early after completing the operation, still maintaining a time complexity of O(k). In the worst case, the algorithm traverses all the digits and performs a swap at the very end. Even in this scenario, the time complexity remains O(k). To confirm this mathematically, the dominant factor in the algorithm is iterating through the digits list, which takes O(k), while the last_occurrence dictionary allows us to check for swaps in constant time, or O(1). Since the inner loop is constrained to a fixed number of iterations, the total complexity scales linearly with the number of digits. Therefore, the algorithm achieves a final time complexity of O(k) and a space complexity of O(k), making it highly efficient for this problem. Common mistakes in solving the maximum swap problem often stem from overlooking key nuances. For example, one frequent error is swapping the first smaller digit with the next larger digit without fully evaluating all possibilities. This approach might seem intuitive but can fail to produce the globally maximum result. Consider the number 2736. Swapping the 2 with the 7 yields the optimal answer, 7236. However, a short-sighted greedy approach could miss this opportunity. Another issue arises when dealing with duplicate digits. If you don't carefully select which occurrence of a digit to swap, you may end up with a suboptimal result. For instance, in the number 1993, swapping the first 9 instead of the second 9 with the 1 gives 9913, which is incorrect compared to the optimal 9193. Lastly, trying to modify the number directly as an integer instead of converting it to a string or array for easier manipulation is a common pitfall. Since integers are immutable in most programming languages, this can lead to cumbersome logic and unnecessary errors. Another oversight is overcomplicating the solution. Many people attempt to use nested loops or advanced data structures like heaps, which can make the code inefficient and harder to debug. The beauty of this problem lies in its simplicity. A straightforward greedy approach can solve it in O(n). Adding unnecessary complexity only increases runtime and risks introducing bugs. It's also crucial to handle edge cases correctly. Examples include single-digit numbers like 5, numbers that are already the maximum like 9876, or numbers with repetitive digits such as 2222. These cases don't require any swaps, and assuming otherwise can lead to incorrect results. Always consider these scenarios to ensure your solution is robust and comprehensive. The maximum swap problem is a great opportunity to demonstrate your understanding of greedy algorithms and array manipulation. During interviews, it's important to explain your thought process clearly, especially when deciding which digits to swap. A key insight is that the last occurrence of any digit in the number is generally the best candidate for swapping, as it maximizes the result. To optimize your approach, you can pre-compute the rightmost occurrence of each digit from 0 to 9, which eliminates redundant checks and makes your solution highly efficient. Additionally, be sure to communicate how you handle edge cases, such as already sorted numbers or numbers with repeated digits. Highlighting these considerations shows that you've thought through the problem comprehensively. The concepts in maximum swap are closely related to other problems on LeetCode. For instance, LeetCode 31, next permutation, involves rearranging digits to achieve the next lexicographical order, which is similar to maximizing or minimizing a number. LeetCode 455, assign cookies, is another greedy algorithm problem where you optimize decisions step by step, much like deciding which digits to swap. LeetCode 738, monotone increasing digits, requires modifying a number to ensure its digits are non-decreasing, a challenge that also involves careful digit manipulation. Finally, LeetCode 121, best time to buy and sell stock, focuses on finding optimal decisions, in this case, the best days to buy and sell, similar to how maximum swap requires finding the best swap to maximize the number. Exploring these problems can deepen your understanding of related concepts. There are several alternative approaches to solving the maximum swap problem, each with its own trade-offs. The brute force method involves swapping every pair of digits and computing the resulting numbers to track the maximum value. While simple to understand, this approach is inefficient with a time complexity of n squared. A more efficient strategy involves using a greedy approach with pre-computation. By pre-computing the rightmost occurrence of each digit, you can quickly identify the largest valid digit to swap for each position, achieving an n solution. This method is both time-efficient and straightforward to implement, although it requires extra space for the pre-computed array. Lastly, recursive backtracking explores all possible swaps exhaustively to find the maximum result. While this demonstrates exhaustive exploration, it is highly inefficient for larger numbers and not practical for most scenarios. Each method offers unique insights into problem solving, but the greedy approach strikes the best balance between efficiency and simplicity. To wrap up, we applied a greedy approach to solve the maximum swap problem, optimizing the placement of digits for the highest value. We learned about time and space complexity, key takeaways, and related concepts. Thank you for joining. Stay tuned for more coding solutions, and happy learning. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!